Most automotive ignition systems use an induction coil to step up the nominal battery voltage of 12 volts to the voltage needed to bridge the gap across the spark plug electrodes. These induction coils operate according to Faraday's law. Relative movement between a conductor and a magnetic field allows 4 ways by which an electromotive force, or EMF, can be induced in a conductor. Move a magnet so that the magnetic lines of force cut across a conductor, as in an alternator. Move the conductor so that it cuts across the stationary magnetic field, as in a generator. Start, stop, or change the rate of current flow in a conductor. This causes the conductor to induce an EMF into itself. This is called self-induction. Start, stop, or change the rate of current flow in a conductor which is positioned close to a second conductor. This is called mutual induction. When any of these methods is used to induce voltage in a conductor, the value of that voltage depends on the density or strength of the magnetic field. The stronger the field, the greater the induced voltage. It is also influenced by the number of turns of the coil. The greater the number of turns, the greater the induced voltage. The speed at which the lines of force are cut also affects the voltage induced. The greater the speed, the greater the induced voltage. In the induction coil, the secondary winding has many thousands of turns of fine enameled copper wire. The primary winding, with a few hundred turns of relatively heavy wire, is positioned close to the secondary. A soft iron core is positioned centrally to concentrate the magnetic field. Current flow through the primary winding establishes a magnetic field around the windings. The higher the current flow, the stronger the field. Sudden interruption of the primary current effectively disconnects the battery from the coil and current flow ceases. This leaves no externally applied voltage source to dictate the voltage value across the ends of the primary winding. The magnetic field decreases, returning its stored energy to the coil by cutting across the coil windings. This produces a self-induced voltage in the primary winding and a mutually induced voltage in the secondary winding. The maximum value of the secondary voltage is partly determined by the ratio of the number of turns in the secondary winding to the number of turns in the primary winding, in this case 100:1, and by the value of the self-induced voltage in the primary winding, in this case 300 volts. Then, if this coil is 100% efficient, the maximum voltage available from the secondary winding would be 300 volts multiplied by 100. That is 30,000 volts. Since the value of the self-induced voltage in the primary winding is also influenced by the rate of change of current flow through the coil, it is essential to switch the primary current off as quickly as possible. All ignition systems make provision to ensure that this occurs.